Hello everyone, this is lecture 44 of PEC. Based on the small signal method of last lecture, we will discuss the small signal models. First, let's review why we need the small signal models. This is a general circuit we discussed at the end of last lecture. We can write its KVL equations. We divided the equation into two parts to solve in the last lecture. The first part is to solve the static working point U0, I0 of the nonlinear resistor. Here is the equation. The solution of the equation is the working point U0, I0. It corresponds to such a nonlinear resistor circuit. Substituting this equation and this solution into the equation, we can eliminate the static working point. Then we get a linear algebraic equation about delta IT and delta UT. That is, when U0 is given, it is a known value. So it is a linear algebraic equation about delta IT and delta UT. Based on the algebraic equation, we can get a corresponding linear resistor circuit. So the original nonlinear resistor is replaced by a linear resistor. The linear resistance is the reciprocal of the coefficient. After solved these two circuits, delta I is added to I0 and delta U is added to U0. We get the final solution of the circuit like this. We finish the analysis of the circuit containing the small signals. For the analysis of such a circuit, the circuit on the left can be solved by the analytical method, the graphical method, or the piecewise linear method we learned earlier. Now we are interested in, is it possible that we don't use the previous procedure by writing equations to get this circuit? Can we start from the original circuit and get such a linear resistor circuit directly, so that it can be very convenient to find delta IT and delta UT and finish the analysis finally? Compare the circuit and the original circuit. They have the same topology. The only change is that each component's parameter may be changed. It does not have to be changed. There's no change for the linear resistance. The source has been changed. The nonlinear resistance has been changed to a certain value. Next, based on this idea, we will discuss a change for each component in a small signal circuit. First, if it is a nonlinear circuit controlled resistor, current controlled resistor. For this case, we might as well draw it UI relationship like this. At a certain working point, there is a small delta I, and we can find its delta U. We can write delta U equals dF over di at a point I equals I0 times delta I. It shows that there is a linear resistive characteristic between delta I and delta U, and the linear resistance is F prime I0. We can draw it like this. Similarly, if it is a nonlinear voltage-controlled resistor, we can also draw its characteristic like this. Similarly, we still use the method of the tangent. This is delta U, this is delta I. Then delta I equals dG over du at the time U equals U0 times delta U. It is a linear algebraic equation about delta I and delta U. We can define it as a dynamic conductance. It is G prime U0. So it is a linear resistor or linear conductor. If you express it in the form of the conductance, that is like this. If you express it in the form of a resistance, that is 1 over G prime U0. Based on the method we continue to discuss for a linear resistor, how is it under the small signal? For the linear resistor, no matter delta I or delta U is a perturbation variable, we can find that its slope is a fixed value. So we can write delta U equals dRi over di at the time of I equals I0 times delta I. For dRi over di, it equals R with arbitrary I0. So in the case of the small signal, it is equivalent to a linear resistor with a resistance R.